All right, let's take a look at this problem, which is a little bit of unusual circular motion and gravity problem. So determine the time it takes for a satellite to orbit the Earth in circular near-Earth orbit. A near-Earth orbit is at a height above the surface of the Earth, which is very small. So we're near the surface of the Earth. So it's like we're kind of like here, but we're kind of like orbiting it, but just barely above the like around the surface of the Earth. Okay, so how do we handle like circular motion problems, forces, gravity, stuff like that? Like how do we analyze a scenario like that? It's a forces problem still. We're still going to draw step 1, draw a free body diagram. You might be like, well, why am I drawing a free body diagram? Well, that's just kind of what we have at our disposal at this point. This is the technique, this is the steps. You don't always know what it is that you're going to be using it for. And that's the key part of problem solving sometimes, is you are going to be following some steps and then you're going to see, okay, can I interpret anything? Do I gain some insight into the problem by doing this, instead of just trying to know all the steps ahead of time, how it's supposed to solve it. Okay, so when we draw a free body diagram, we have gravity acting towards the center of Earth, right? That's our rule for gravity, acts towards the center of the Earth. Now, we're orbiting it, so there's nothing else actually touching it. So that's like the only gravity. Actually, I should write it as force of gravity here, by the way. Now, you might be confused sometimes, because when we do this unit with circular motion, we talk about Newton's law. There's 2 forces of gravities we use. One is mg for near the Earth's surface. And if you are far from the Earth, for the far from the Earth's surface, we use this one. This is for far from the Earth's surface. So those are two different things that we're going to do. So in this case, we are near the surface of the Earth, so the Fg does equal mg. Okay, so we draw the free body diagram. We identify the acceleration. Now, is the A 0? Is it moving? Now, this is moving in a circular path. It's orbiting the Earth. What kind of acceleration is that? It's acceleration towards the center of the circle. We call centripetal acceleration. And 3, now we're going to do F net equals ma. We also have to establish directions and decompose forces if you have to, but we don't need to do that. We only have one direction. The only one force here is mg, and that equals m. Now the A is centripetal, so we write that as v squared over r because it's moving in a circle, right? That's the only difference in circular motion, is that if it's centripetal acceleration, like if it's moving in a circular path, then there's centripetal acceleration directed towards the center of the circle. Okay, you can see the m's cancel. And what can we solve for at this point? We can solve for the speed square root of rg. Okay? Now, what does that tell us? What do we know about that point? We want to know the time it takes to go around here. So how does the speed that we travel relate to the time to go around once? Speed is actually distance over time. Right? If you think about that, if you take enough time to think about it, you're just like, well, the speed is the distance over time. What's the distance we travel? The circumference of the circle, which is about 2 pi r. And then the time is what we want, the time to go around once. Okay, so then we can solve for t now. Multiply by the t and divide by that. It's going to be 2 pi r over root rg, where r would be the radius of the Earth. Technically the radius of the path, but because it's so close to the Earth's surface, about the radius of the Earth. And that would be our equation there. You could plug in some numbers if you knew the radius of the Earth, and then g of 9.8, and then that would give you a number in seconds. Does the result depend on the mass of the satellite? No, because the m's canceled over here. Does not depend on the mass. That's why when you're orbiting the Earth, you could be a giant spacecraft, you could be a little piece of rock, you could be a little screw, a bolt, debris. They're all going to orbit with the same speed, around the Earth there.